Okay, good morning. And I'm Ji, the coordinator for Center for Complex Systems. And welcome to our Masterclass, the second edition. And this Masterclass is generally supported by one of our alumni, that's Lawrence Harrenstrom. And today we're very happy he's also here. Let's thank him for his generous support. This Masterclass, we created this series. The idea is to give you sort of a crash course on a specific topic on complexity science, and which can generally use in many fields. And today's example is really a good example. And today we are going to talk about extreme events, because now we hear a lot from the news, like the hurricanes just passed through the Florida, and the heat waves this summer, we also suffer a lot, and also the financial crisis. We always worry about what is going to happening or what happens in the past. So we can see that the analysis of extreme events can be used in many fields like physics and chemistry, biology, and the economics, etc. So today we are very happy we got a leading expert here to talk about the extreme events. And I will allow our director of our center to introduce our speaker, and please, Henk.
Yeah, so I'm Henk Dijkstra. I'm the director of the Center for Complex System Studies, and really pleased to have Tobias Grafke here for the whole week. He got his PhD at the University of Bochum, 2013, and then did postdocs in Weizmann Institute and in Courant. So those are fantastic places to be, particularly on the subject. He's a young star in the field of, a relatively young star, in the field of, say, extreme events, and has made many important contributions to this field. So we'll give three sort of lectures, right, and with exercises. So today is more the general introduction to the topic. So it should be easy to follow for many of you.
No, it's good.
And we'll get into more detail tomorrow and Thursday with also exercises. So Tobias, we're really curious.
Yeah, thank you for the introduction. Thank you for giving me the opportunity to speak here. And yeah, I'm excited to talk a bit about extreme events and rare events in complex systems. As was just said, this is the first of 3 lectures, and today I'm not going to use the blackboard, but tomorrow and Thursday is going to be a bit more hands-on and a bit more derivations and a bit more like trying to get into the technicalities of stuff. Today is more like a motivational or introductory talk. And so the next 1.5 to 2 hours, I'm going to talk a bit about the main ideas of what we're going to see over the week. So we already heard a bit of an introduction on why we should care. So I'm using rare events and extreme events interchangeably here, and that's maybe a bit of a questionable choice. That's, I think, what was meant when we were just discussing, but it's also the distinction that I want to make is extreme somehow implies that it's something big, while rare is a statement about its probability. But in any case, somehow, if you are having the philosophical question on what kinds of events should you focus your attention on, I guess what everybody concludes after a while of thinking about this is somehow what is important is the product of the impact of the event multiplied with its probability, right? If you have something that happens a lot, it doesn't have a lot of impact, but it still happens so often, you should care about it. If it's very rare, you might not care, except if it has a very big impact. So if we have events that have very low probability, so that they're typically not observed, but in the rare case that they are observed, they are very impactful, you might still want to care about them. So there are very typical examples of that. We heard a few, but maybe earthquakes, stock market crashes, plane crashes that happen very rarely, but if they do, I mean, you want to mitigate for them nevertheless. Many of the events that I'm going to talk about are of this class, but there is another class that's maybe more unfamiliar generally, or maybe less intuitive. And that's the one where you have a separation of scales. You have multiple scales, maybe multiple time scales or something like that. And on the intrinsic scale, for example, on some thermal fluctuation scale for chemical reactions, the event is very rare, but for our everyday life, it's very common. And chemical reactions are a good example of that. You have a couple of reactant molecules that then react into a product molecule, and they need to bridge an energy barrier for that. And it happens on the order of seconds. But in order for this to happen, because it needs to bridge this energy barrier, it needs to try millions, billions, trillions of times, but the intrinsic time scale, the thermal fluctuations that are intrinsic to it, are so fast that you have so many trials that eventually the event will definitely happen. This is exactly the situation that is the most easily treated, because at the same time you have a ray event, but you also have observability on human timescales still. So it need not be a timescale separation. For example, I put there bit flips from cosmic rays as well, where maybe you have like a bit that stores some kind of information and a cosmic ray hits it and flips it around. This is very rare to happen, that there is like a supernova somewhere and then it exactly hits Earth and then the bit flips. But if you have a hard drive with 10 to the 9, 10 to the 10, 10 to the 12 bits, eventually it happens quite often. And there was a transition time, it's probably already like a decade ago, where the number of bits in a computer was high enough that these events needed to be taken into account. And nowadays they so regularly happen that everything's like error corrected anyway. So both of these can be treated with similar methods, and both of these are relevant in different kinds of situations. In both of these cases, the central problem is that rare events are difficult to deal with in complex systems. If your system that you're considering is of a certain complexity, such that you cannot easily talk about analytical solutions, or that you cannot easily on paper compute these kind of things. For example, if you have coin flips and you have like, what's the likelihood of 1,000 coins showing heads, you can do that on paper. That's not problematic. But if you're talking about the climate, or if you're talking about some atmospheric flows or stuff like that, the only thing that you can do is numerics or experiments. There's no chance ever in getting any kind of estimates on paper that are anywhere close to reality. So the central problem here is that these events are far too complex to somehow treat analytically, and on the other hand, they are far too rare to be observed in an experimental setup or in numerics. If you have something that happens 1 in a billion times, then you need to do 1 billion experiments in order to observe it once. If you want to do statistics on that, you need to have thousands of billions of experiments to do it, and that's usually prohibitively costly. And the same goes for simulations. So you somehow need to be smart about it. You somehow need to try to figure out some commonality of them, or you need to somehow have some external input in order to make them more treatable. So this implies developing some kind of theory of rare events, and also implies maybe developing some kind of algorithms in order to do. And that's going to be a focus of this week in any case. Most of what I'm going to say about applies to simulations of things. So you have a naive way of simulating something that's very intractable, and then you're trying to somehow modify it in a way that you treat these rare events in a more specialized way, and this will result into so-called rare event algorithms or rare event techniques that deal with this in a specifically designed manner. So this is the central problem, and this is what I'm trying to address. And I'll basically introduce 2 classes of commonly used techniques, and these 2 classes of techniques will be discussed Tuesday and Thursday, but I'll kind of like showcase and hint them today. But first, I want to introduce like a few examples of where I came across this, or where this has been come across in the field. The first and maybe simplest example is ship capsize, ship rolling motion. This is a very, very easy system and very easy to understand. So the sketch on the right-hand side is supposed to be the hull of a ship cross-section. One second. And the most naive way to model this is you say it has a center of gravity, that's the red dot labeled with G, a center of buoyancy, that's basically the center of gravity of the displaced quarter. And those two have opposing forces, which lead to the ship move somehow on the water. The precise nature of how this works is maybe a bit harder to derive, but what you can imagine is that this is some kind of pendulum. If the sea would be flat, eventually the ship would be upright. But if you somehow change the angle a bit, it will oscillate. And the oscillation is very nonlinear because the whole shape is very complicated. And of course, ship hulls are designed in a way to make this oscillation beneficial, and there will be friction. So what I should use the stick, I guess. Phi is the so-called rolling angle, and phi will behave like an oscillator, and it has an angular velocity, which I call phi dot. over which it oscillates, some friction, and maybe even some stochastic forcing, because in the end I want to deal with stochasticity. So these two differential equations, these are stochastic differential equations, but don't worry if not seeing that kind of form of writing them, describe the motion. That's basically saying how the angle moves with the angular velocity, and the angular velocity has a restoring force that comes from the hole shape, friction, and both of them have noise associated with them. Whatever the precise form, we can make a plot of this system in the phi dot plane. That's what I'm doing here. So this is the rolling angle, and that's the velocity. And these arrows somehow signify the deterministic part of the equation that I've just shown. So the part of the motion that we can predict, and that's non-stochastic. And it's somewhat intuitive. So the angle equals 0 means the ship is upright. And if you perturb it slightly, it will do these motions in a circle or in a spiral that slowly decay into the 0 again, which is just an oscillator having a smaller and smaller amplitude until it's upright. If you perturb it by a lot, it will still do that. But if you perturb it by too much, eventually it will instead go onto this other point. So there is a second fixed point of the whole system, which of course corresponds to the ship being capsized and being on the opposite way around. So you could say that this is the place that we want to be in. That's the place that we possibly want to avoid. And the question is that if I now add stochasticity on that, in this case, very non-physical, easiest mathematician assumption of having just Brownian motion added on top of that, how would the noise eventually push you over to the other side? How would the waves maybe push over your ship? So this is the problem of intact ship stability. How likely is it, or on what timescales could we expect just the randomness to kick our ship over? And the corresponding probabilistic question you could phrase like that, conditioning on the fact that we start at the green dot or in the green region, how likely is it that we will reach the red region? And the most naive way that you can think of experimenting with this system, meaning implementing it with a computer, is you write some kind of program that integrates these equations a lot of times, and then you just observe how often that happens. And if we do that anyway, we can go one step further and look at, if it happens, how does it happen? And here's an experiment of that kind. I did like a million simulations of this system or so, I don't know, on my laptop. And whenever the capsize happened, I recorded that event. And what you see here, this cloud, is somehow like a transition trajectory density plot in the configuration space. Meaning that if these capsize events happen, they spend a lot of time here, they're exploring a bit around here, but then they somehow flip over and then they are capsized and explore a bit over there. And the thing that I want you to notice is that even though around the fixed point, of course, these are just clouds of points, that's just because usually you would either be here and wiggle around or you would be capsized and wiggle around. But between the two sets, there's a very common way of these events happening. So the observation is that all transition events happen in a very similar manner. There is some kind of transition tube, if you want. That's in the example of the pendulum, or of this, I mean, it's basically a pendulum. In the example of the ship rolling motion, a very natural thing to think. So all that's happening here is that the velocity goes down until you hit this unstable fixed point. That's basically the ship being exactly at the critical angle, where a tiny kick in one direction will put it in this back in this spasm, but a tiny push in the other direction will flip you over. And as you approach that point, you would get slower and slower. But once you've crossed the point, you are speeding up. So it's very natural to think that all the events happen that way, as opposed to, for example, going down here, which would basically mean even though your velocity is negative, you somehow still flip over, which is very unnatural. But the idea is that a similar principle might apply to far more complex systems, where you still have all the events happening in a similar manner. And I'm going to jump from this two-dimensional system directly to a much, much higher dimensional system, and that is Earth climate. Maybe the most complex system that scientists nowadays deal with. So what you see here is the simulation of the climate of Earth over very long times. This is some kind of intermediate complexity model that has maybe 100,000 degrees of freedom or so. But it's enough degrees of freedom to have, for example, the continents embedded, ice cover, water, wind, and so on, temperature. there is stochasticity added to this system in the form of a fluctuating solar constant. And then you just observe this stochastic system somehow equilibrate over very long times. And what you see is, well, you observe the state that we all know, that's our a very coarse-grained approximation of our planet and the climate of it. But there is a second state that you observe, and that has been in the media multiple times, the so-called Snowball Earth state, where all of Earth is covered in ice. This is a valid and feasible state of our planet to be in. At the moment, we are not in it, but if we were, we would stay there for long times. And the reason is the so-called ice albedo feedback, in the sense that if the whole planet is covered in ice and snow, it's much more reflective and less sunlight gets absorbed by Earth. So Earth would be colder, meaning that it stays ice covered. While if it's in the current state, the oceans absorb, or like the non-white color of Earth absorbs a lot of incoming radiation, therefore the Earth stays hot. So both of these states are locally stable. Both of these states, if we are in them, would remain like that for extended periods of time. And this is exactly why there is a fluctuating solar constant added, which is arguably unphysical, because the solar constant doesn't really fluctuate, maybe with the exception of volcano eruptions and these kind of things. But here, this is in order to drive the system from one to the other. And this you can do. Oh, yeah, that's a question.
Very naive question. So in both examples that you've discussed so far, you're not talking about extreme events that lead to these states, right? It doesn't have to be an extreme fluctuation in the solar radiation that leads to these, or the lack of, that leads to the snowball.
They are included. I mean, I haven't specifically said the words, but they are always associated with stochasticity, and the stochastic forcing, or the driving force behind them, must be present in order to facilitate these flips. So for the ship capsize, this is associated with a certain wave packet or whatever on the ocean that will kick you over, and it will always happen also in the same way. I've just looked at it from the perspective of the state variables instead of the stochastic variables. But
Thanks.
and here it would be the same. It would be a specific fluctuation. I mean, I guess it would be very cool to go from here to here. I mean, it's not that hard to imagine what the stochastic thing does, but it's much more interesting to see what the high-dimensional system itself does. So,
So does
yeah.
can this only happen when your mean solar constant is within a certain regime? I suppose so. Huh?
The multi-stability,
Yeah.
that's certainly true. Yeah. I'm not sure, but including the realistic one.
Yeah.
So if you simulate the system for a long time, you might hope to observe these transitions between this state and that, or the other way around. And this is exactly what has been done here. So in order to observe even what is happening, what we want to do is we want to project this very high system that has, as I said, maybe 100,000 degrees of freedom onto only 2 degrees of freedom. One of them is the mean surface temperature. That's just the average temperature of the planet Earth on the surface. And the second is the temperature difference between the equator and the pole, with the intuition that this one is probably lower or higher for the two states. So is this one to a degree, because in one case you have ice on the poles, but not on the equator. In the other case, you have ice everywhere, so the temperature difference is much lower. And if you then let the system run for a long time, you can kind of get like a probability density plot in these two variables. And here is how it looks like. So this is the equator pole temperature difference, and that's the mean temperature. And this whole area, and including this local minimum here, is the state we are currently in, with the mean temperature around like a bit lower than 20 degrees, and that's the corresponding equator pole temperature difference. But there is this whole other region, this whole cloud, which corresponds to this snowball Earth state. And indeed, if you then look at how transitions happen between the two, that is, how do you transition from our current state into the snowball Earth state or the other way around, you can average these transitions out, and the red one is the one from snowball to warm, and the blue one is from warm to snowball. And indeed, what you observe is that, again, all these transitions happen in a very similar way. So every time we observe cold to warm transition, it happens in a very similar way, and the red line is kind of like the placeholder trajectory that shows this, as is the opposite direction, even though forward and backward individually happen completely different, because there are completely different physical processes involved in the Earth freezing and the Earth melting. So the last system that I wanted to get at is rogue waves. These are extreme events on the ocean surface. So you have an ocean, the ocean has some kind of elevation, and you ask the question, how likely is it that an extremely high wave will hit my ship, or that I will observe an extremely high wave? And there is somewhat funny anecdotes around the whole topic of rogue waves, simply because up until maybe 50 years ago or so, it was widely believed not to exist at all. So that rogue waves weren't really a thing. And that stories of sailors that came back and talked about 20, 30 meter high waves were just telling stories and not really observations of the reality. And this was in part because of, I guess, survivorship bias and the fact that if you observe such a big wave, usually you would not survive to tell the tale. And that only recently changed with the advent of much bigger steel ships that are able to survive any kind of wave that happens on our ocean. And the other thing is, of course, that there was much less data around, only stories. This changed maybe in the 50s, 60s, where people were maybe carrying cameras and there were more systematic measurements of the ocean surface. And this is one very famous picture of taken from the bridge of some, I think it's a gas tanker, as a large wave approaches it. And it's a bit hard to grasp the scale, but I think this tanker had, the deck is usually, if the sea would be calm, order of magnitude 10 meters above the sea level. So this wave is 20 or 30 meters high, and it will eventually hit the bridge where this photo is taken from, even though the ship did survive. The bridge was destroyed, or at least the windows of the bridge were destroyed. And on the bottom, you see maybe the most famous wave event in recent history is the first one that was recorded by a scientific instrument. That's the so-called Droughtner Wave, where the Droughtner platform is some kind of platform oil rig, I think, in the North Sea. And they had some kind of measurement apparatus, I think like a downward pointing laser that just records the ocean surface elevation as a function of time. And that's the signal that was recorded. So here you see time in seconds, and here you see elevation in meters. And the blue line is exactly what the ocean surface does. So you see that the sea is very violent already here, because it goes from maybe -4 to +4 meters. These are 8 meter high waves. It's not nothing. But then comes this one event that is just so much bigger than all the surrounding ones. So this is crest to trough above 25 meters wave, that you would think this thing can never happen. So the mathematician's argument for this to never happen is that you say, okay, these are waves. I know waves, right? This is a linear equation. The only thing that can happen is superposition. You can easily measure the distribution of different frequencies in the ocean, and then I just need to multiply up probabilities of different frequencies somehow aligning in a certain way. And if you do that, if you basically do the linear approach, if you say the Earth would, the sea would be a linear system, these waves would be very much more unlikely than they actually are, like thousands to millions of times less likely than they indeed are, which means that you would never observe them. So it is still fair to say that the full mechanism is not understood on how these waves happen. That's maybe also a function of the fact that it's not quite clear what you even mean with the question. These are waves in deep ocean, but do you talk about currents? Do you talk about winds, or is it just out of nothing? The traditional rogue wave is one that happens in calm sea and without anything happening in between, but there might be like underlying crossing currents in the ocean itself that you don't really know about. These kind of things become very technical and very physical, detailed very quickly. But in general, the question is, how can it be that the likelihood is so much higher than the linear system? There must be some kind of nonlinear amplification mechanism present. And there are candidates for that happening. What we care about more from the end user perspective is what's its probability density function. What I want to know, or maybe what an insurer wants to know, is, well, how likely is it that they happen and that they hit the ship? And it's not a completely separate question, because if you understand the mechanisms, maybe you can create probabilities, but it's a different phrasing. I'm not asking necessarily about the physical mechanism. I'm mostly asking about its likelihood. So I'm asking about the tails of the ocean surface elevation probability density function. So just to introduce a bit of notation, for this system, we saw just such a data series for the Droughtner wave, and now I'm showing you something that was a fun project of mine. It was actually the only time I ever did something that had an experimental component to it. So this is a signal coming from the experiment, where you also have an elevation signal as a function of time. This is in seconds, and that's again the elevation in meters, just much less impressively so, because the elevation here is minus 0.1 to plus 0.1 meters. So the waves are this high. You can still reasonably talk about rogue waves and a rogue wave threshold by the accepted definition that's nowadays given, namely if eta of x and t is your surface elevation, you say the significant wave height is 4 times the standard deviation of eta, that's the red region, and then the rogue wave threshold is twice that. So this makes sense both in these wave flumes that have very low amplitude waves, as it is on the ocean, where the kind of range of waves that you can observe is also very different, depending on external conditions, right? As we just saw, there were 8-meter waves and then a 25-meter wave within the 8-meter waves, but sometimes they're just 1-meter waves, and then you get hit by a 4-meter wave, which is also similarly a rogue wave event. And this kind of rescaling works very nicely in many aspects of fluid dynamics, including these kinds of surface wave equations, just because you can scale everything up and down by redimensionalization. So this is the same idea that you say we can put a model of our plane in an air, in like a wind channel or something like that, in order to make measurements, and then just scale everything up, and the same thing applies with a very well-known like rescaling procedure. The same applies to these wave equations. So even though these are just 10 centimeters high, they are of the same nature as would be ocean surface waves if you exclude effects like wave breaking or capillary effects of these kind of things. The other thing that I want to stress is that twice, 4 times the standard deviation is 8 times standard deviation. This is a ray event. You would think so. Okay, so given that, here's the experiment that was performed. This is a very long wave flume in Norway. And on one end, it has a wave maker that pushes in a random signal to generate waves that then flow along this wave flume until they hit the beach. And the beach is shaped in a way that there's as little reflection as possible, so that there's only waves going from the wave maker to the beach and not back, and there are no standing waves. These waves are planar. This is the whole plane, so the width of the channel basically doesn't matter. You just want to exclude boundary effects from the left and the right boundary. And then you distribute probes along the wave flume and record elevation signals such as the one that I've just shown. So, and then the argument why this is a good model of the sea is basically given through what signal do we even put in. And the signal that has been put in is one that's statistically indistinguishable from the ocean. So there had been a project already in the 70s, basically just recording what is the energy distribution across different wave frequencies in the ocean. And here's one such plot from the 70s, where you have the frequency and the corresponding energy located in that frequency. So there are multiple curves here corresponding to multiple physical situations, meaning that there were different kinds of wind speeds, different kinds of distances that the wind was able to blow over the surface, and so on. And this gives you different distributions, and these can be parameterized and put in. From a mathematician's point of view, you would rescale everything, you would clear it of all dimensionality, and the only 2 parameters that remain are the significant wave height that we just introduced. And the second is a non-dimensional parameter that somehow quantifies how nonlinear the system is. So you can make the waves higher or lower, and you can make your system more or less nonlinear. These are the two things that remain for this input system. And this was put in on one end of this channel, and then observations were taken here in order to observe the waves. So the precise way that these observations happen is the following. This is a somewhat complicated plot, so let me unpack it. This is time. T is time in seconds. And this is position in meters along the flume. And the third one is what is recorded as measurements. This is the elevation. So we have a probe at 10 meters, at 30 meters, at 45 meters. Each of them is recording a signal. And then randomly we say the 45-meter probe, let be our probe that we are looking at. We define a threshold, for example, the rogue wave threshold, or maybe even a bit higher. And whenever this threshold is exceeded, we call such an event, here colored in red, a rogue wave event. And it is one according to the definition of the exceedance of the threshold. We record the whole package. But because we also know the group velocity of your wave packages along the flume, we can then take a look at how did these wave packages look like before the event happened. How did the wave package look like at the 10-meter probe that eventually, after like 20 seconds or after 35 meters, will develop into a rogue wave? We get some kind of history. Of course, not a continuous time history, but at least we get a few points. So what we can do then is we can not only build a collection of extreme events, a collection of rogue waves, we can also build a collection of extreme event precursors. And then the first kind of statistic that you would want to do is maybe, well, how do the rogue waves look like and what are their statistics? And that's what you see on the right-hand side here. The solid red line is the mean of the experimental measured rogue waves, that is of the signal conditioned on the fact that you observe a high amplitude wave. Here, this was roughly the threshold, maybe 20 centimeters. And in solid red, you see all of the lines that exceeded that threshold. Here's the same wave packages, just at the earlier probes. And the thing that I want to draw your attention on is that the red shaded region, which is plus or minus 1 standard deviation around that, around the wave package, there's basically no variation. Far from it, everything averages to 0 and everything has some kind of variance. That just means everything is decorrelated. But around the wave, everything looks very similar. So the interpretation that I want to put forward here is that if a rogue wave event happens, the whole area looks very much alike every time. So you only exceed the threshold here if you also do the stuff here, at least roughly the same thing. And this applies in a similar, maybe a bit less strong, but similar way for the precursor events as well. Every time an event happens at that point, at that time, earlier you have a very similar shape of your wave. So yet again, the idea is, if I condition on something rare, the events happen all very alike. And that's somehow the thing that we want to tease out on this day, maybe. There must be some story about this, yeah?
Yeah, just probably somewhat off topic, but it looks very much like stochastic resonance. Is that correct?
I would say I don't think so, and maybe this is something to discuss offline afterwards. Stochastic resonance in the... I don't think so. I mean, I didn't even specify what the stochasticity in the system is. And I mean, I did somewhat, but yeah. Yeah, but maybe we should discuss it. So what I wanted to hint at is that there must be some kind of part of the story where I say, as soon as something is very rare, it happens always in a very similar manner. Can we somehow get out of the system what this manner is? And can we use this maybe to predict its probability as well? Okay, so these were the 3 examples that I wanted to give. And that's maybe the conclusion of this introductory part would be rare events are often relevant. We might choose them to be relevant depending on their impact. And they do occur in many real-world systems. But crucially, if they happen, they often happen in a similar way, around a typical transition tube, if you will. So not all of them are transitions. Maybe this is a bit of a stretch of the term. Clearly, you could say this was the ship capsize, that this is, or in this case, it's a proper pendulum that's symmetric. This is a transition from one state to another, as was maybe the Earth climate. While the rogue wave not necessarily is a transition, because the rogue wave thing is only very transient. It pops up but then disappears on its own. But in both cases, there are typical ways that this can happen, and typical ways in which I transition into this event. And the main questions that we want to analyze I think this is just my machine. The main thing that we want to analyze is how often do they happen? That is, what's the transition probability? And also, if they happen, in what way do they happen? That's maybe what you would call the transition path ensemble. Also to explore mechanisms, or maybe to prevent them. If you can prevent the mechanism, you will prevent the rate. So all of these are probabilistic questions. And for basically every system, they can only be answered numerically. All right. So the first thing that the maybe most naive thing that you would want to do here is direct sampling. And that's what I wanted to start off with. that's maybe most of you have come across this idea, or maybe if not, then maybe that's the first idea that you would have yourself, even if you had wouldn't have had any kind of experience or prior knowledge on it. The easiest way to obtain an estimate of any probability is to just repeatedly try and count how often it happens, right? If you have some system that you can let go again and again, and then you ask how likely is it that something specific happens, meaning what's the expectation of some event X, you just do capital N experiments Xi, and then you average. You basically say, okay, it happened, it didn't happen, it happened, it didn't happen, maybe it's roughly 50% probability. This is an instant of a Monte Carlo method, and maybe that's a nice time for me to play around a bit. That's why I'm here for in the end, to demonstrate how that works. So hopefully, because my connector is a bit shaky, this does work. So what I have here, can you see my screen here? This is just MATLAB here. And on the left, I can write a program. So I want to now do some kind of coin toss experiment. That's, I guess, if the probability starts with everything, they always start tossing coins. So MATLAB has a function that's called rand that gives you just a uniformly distributed random number between 0 and 1. So we can say a coin is something like the question on whether this uniformly distributed number between 0 and 1 is lower than a half. Sometimes I get a 0, sometimes I get a 1. Right? So if I want to maybe throw a lot of coins, I could say coins are something like 10 coins being less like this. So if I run this, I get 10 coins. 1, 0, 1, 1, 1, 0, and so on. Maybe we do it a bit more systematically and say we have a variable that's 10 coins, maybe 100 coins, and I throw 100 coins. So clearly, if I throw 100 coins, roughly half of them will be heads, and roughly half of them will be tails. So we might, for example, ask, what's the likelihood of some percentage of them that's not a half being heads? Maybe let's say the ones are the heads and the zeros are the tails. So if I take, I mean, this is just zeros and ones. So if I sum this up, in this case, I have 49. Well, that's close to the predicted mean. 49 heads. How likely is it to have, for example, 75 heads? That's clearly not the typical case. You would expect typically to have around 50 heads. 75. It's not 100. I mean, that's clearly very rare to have 100 heads in a row. But how, or not, yeah, all of them be heads. But 75 is only like 3/4 of them. So it's maybe rare, it's maybe not so rare, maybe something that we can deal with. The way that I would try to get this is the sum of the coins, that's just the number of heads, being bigger than 75. So I can just run this, and it will tell me 0 because it didn't happen. But maybe if I try often enough, maybe eventually it will happen. Let's suppress the output here. So no, it didn't. No, it never did. So maybe what we should do is something like an experiment. Maybe I do it 100 times. So that's just a for loop. And experiments. So 100 times I will throw 100 coins. And then if the thing happens, I say it happened one more time. Total is total plus 1. Something like that. I need to start with 0. And we basically already have a Monte Carlo sampler, right? I'm doing 100 times my experiment of throwing 100 coins. And then if more than 75 of them are heads, I add 1 to the total. So I guess the probability of the thing happening is total divided by n experiments. I've just counted how often it happens, divided by how often I try. This should give me the probability. Maybe some of you know probability already, they did it already on paper, because you can clearly compute this probability on paper, but I want to play around. So 100 experiments. What did I do incorrect? This is line 5 for E. So it didn't happen this time, even by if I try 100 times, maybe if I try a few times. So maybe I should do 1,000 experiments. still number. So the 0 just means this is the output of that. And it says the total divided by an experiment is 0, meaning the total is 0. So maybe I have to try 10,000 times. So this, somebody tell me the mistake that I made? 100,000 times I'll try. Is there something? Maybe I try 1,000,000 times. Now we need to wait a bit. Maybe try 10 million times. There you go. So that's maybe, I don't know whether you get any intuition, but you need to try 10 million times in order to observe 75 heads out of 100 coins. And we're still waiting. It still happens only once. Yeah. So it says, because I observed it once in 10 million, the answer that it estimates is 10 to the minus 7. So first, clearly this is a real event, but yeah. Second, also it takes a while. I guess the point that I want to make with this is maybe the first, computers are awesome because, I mean, this was just 10 lines of code. In the end, what I did was not only throw 100 coins, try throwing 100 coins and noting down how many heads you have, but I did this 10 million times on a laptop, and it just took maybe 2 or 3 seconds. But the second point, and I guess the point that's much more important for this lecture, is sampling rare events is really hard. This was a rather simple question. Maybe you wouldn't expect it to be that difficult to answer. Still, you need to do 10 million experiments in order to observe the event at least once. I mean, I guess I was lucky because it could have even not happened the first time I tried 10, right? Did somebody try to estimate the full probability, like with n choose k and 1/2 to the 10 and stuff like that? You will not use that. So what you want to do instead, if you want to do something, is you want to use some sampler that is specifically crafted for these rare events. And the main idea is, and we will not get much more deeper than the main ideas, is that you somehow want to bias your system towards the event and then correct for that bias. So there is a number of ways that you can do that. One is importance sampling, which is basically saying I have a higher likelihood of sampling events that are important for what I'm trying to predict. And the other is so-called cloning methods or particle methods, and so on. All of these effectively make the rare event more likely and thus reduce the variance of the sample. So we will get into this more technically in the end. The problem of this is not only that I needed to wait a long time, the problem is that if I would have done the experiment twice or 3 times, the answers would be vastly different because it only happens 1 in 10 million times. The fluctuations are extremely high and the variance will be extremely bad for these. So making the extreme event more likely seems trivial, and then you just correct for it. But the main purpose of that is to reduce variance. So I want to highlight in this talk, in particular, the last way of doing it, the cloning or particle methods, by giving you a more concrete example of these. So here would be, again, a stochastic differential equation. I left it arbitrary. You have some deterministic drift B. You have some Gaussian random noise that's given by these Wiener increments. If you don't know precisely what that means, it doesn't matter. It's just supposed to be some kind of stochastic system. And I guess all of the systems that I've shown you, the road waves, the climate, or the ship, all fit into this framework. You can always write them as some kind of differential equation with stochasticity. In this case, I just want x to be a real number so that I can plot them nicely. So this is the time axis, and that's the axis that gives me how high my x is. I start at the point 0, at time equals 0, and then if I sample the system, meaning that I simulate my system once, like intuitively this corresponds to one trial, like one coin toss thing, but here I need to integrate a different equation, it's a bit more costly. I get a sample trajectory. So this would be what the system does. I didn't tell you precisely what the system is, but some kind of system does this. It fluctuates around, and in the end, it hits somewhere. It looks a bit like a stock market price or something like that, and people do simulate them with similar stochastic differential equations. In the end, though, what I want to hint at is, for example, what is the probability that at the final time, x capital T, that's the end of my temporal interval, I exceed some kind of threshold? What's this likelihood? So this might be important for boring things like option prices and so on, but that's also important, of course, for example, for the snowball Earth, right? What's the probability of having a temperature that's smaller than some kind of threshold, for example? How likely is a heat wave in Central Europe? How likely is it to observe a certain rogue wave? They all fit into this threshold, right? Maybe not x of t bigger, but some function of x of t being bigger. But it's this kind of thing. So if I would employ the same kind of thing that I just did in MATLAB for this system, I would just do a lot of trajectories. So I did that here. That's maybe 30 trajectories. And then the thing that I need to do is count how many of them exceed my threshold versus how many don't. Maybe the first line here is my threshold, and those two exceed the threshold and the rest don't. So if this was a total of maybe 30 trajectories, my estimate of the probability with my naive Monte Carlo sampler would be 2 in 30. Of course, if I set my threshold to be something extreme, it would be 0 in 30, and I would have nothing, and I would need to rerun the experiment a lot of times, maybe again 10 million, maybe much more. And you quickly, very quickly, run into regions where your runoff is exponential, and you have no chance of ever observing the event. Okay, so what is the answer of that from the cloning method perspective? Same differential equation. This is called under the umbrella of genealogical particle algorithms, and maybe you will get a hint of why that is the case. We would still simulate the system. We would still simulate it multiple times, in this case 4 times, but we wouldn't simulate it the whole way. We first simulate it for a short amount of time, maybe a third of the temporal interval. And then the major ingredient of these kinds of algorithms is some kind of score function, reaction coordinate, some kind of function to evaluate whether we are on the right path or not. For the rogue waves, that might be the highest envelope that we've seen so far, or maybe for these climate applications for a heat wave, that would be the current mean temperature in a region or something like that. In this case, it should probably be, because we want to exceed certain thresholds, it should be this axis, and also we don't have any other degree of freedom because it's a 1D system. There's only one variable that we can look at. So I rank these according to how high have they climbed already, and the higher they have climbed, the more likely I'm going to be happy with them, meaning that the more likely I'm going to keep them around. So in this case, these two, because they are above 0, I say they do what I want, I keep them. Those two I kill off. I don't even bother trying any further than that. They are already not doing what I want, I throw them away. These two I keep. But of course, if I would continue doing that, eventually I would kill all of them. So what I do with these two is I say, they are doing nice things, I split them, I copy them. It's some kind of genetic way of saying these are more to fit to the purpose than those are. So these are trajectories that are in the ensemble that I'm aiming for. So I split them again to a total of 4, because I guess that's the number of CPUs I have, or some other kind of hardware implementation threshold, and would randomly assign copies of them depending on how well they perform. So in this case, each of them may be split into 2, and I do another part of the simulation. So some of them went back, some of them went even more extreme, and again I rank them according to the reaction coordinate or the score function. In this case, I pick those 2. So it doesn't always need to be the highest 2. It's maybe just like a probability that's higher if they are scoring better and worse than if they're scoring lower. But in this case, again, it works out to be exactly the utmost 2. And I would also split them according to their performance. So if we do it the last time, I split this in 3 and this just in 1 again, but it survives. And those 2 will be killed off. And then I'm done. And now I have generated samples of the same system that are scoring much higher in terms of whether they exceed the threshold or not. Of course, it's somehow cheating, right? I've pushed the system towards it, but I cheated in a very controllable manner. Namely, that I just discarded those that I didn't want to consider. And I know how many I discarded. So in the end, I can still add up what this amounts to. So the final answer that I want to compute needs to correct for this bias, but it's not difficult to correct for the bias. I mean, even though I've fiddled with the system, each of these trajectories still is a solution of the stochastic differential equation, right? At no point did I somehow change the physicality of the system. This was all the same. I just somehow selected the ones that I liked. But if you just, in a specific manner, add up all the trials that we have, including the ones that have died off, and including the ones that could have been if I wouldn't have killed them all, you get a very similarly looking estimator that looks a bit more complicated, where I say the probability of exceeding a threshold is again a sum, but now the weights are different. They are no longer 1/n, each of the simulations I do has equal weight. Now I'm saying, because this has split multiple times, it's somehow like a less strong weight. So the extreme case you can already imagine, for example, for the coins, is maybe all of them do exactly what I want, and all of them have a much lower weight than 1. So in the end, I get an answer that's again the right one that should come out. So this doesn't seem so complicated, I feel. But the most important benefit of exactly this method is the following, namely that at no point did I need to change my equation. If I had some complicated code given to me by like a bang, and they say, we won't tell you what it's doing, but can you somehow estimate relevance with it? You can, because all that I need to do is run it for shorter times, but usually you can do that, and then evaluate the output. I at no time need to go into the code and somehow change it around. And that's exactly why this method is the method of choice for many rather complicated algorithms. For example, in climate, you would just take a climate code from someone that's smart in climate and has already spent half of their career implementing that code, and then you just evaluate the outcomes and copy them or discard them, and you get bias dynamics, and you can estimate them. So one very nice example of that I wanted to give.
Maybe it's a good time to break.
All right, yeah.
Shall we break for a few minutes?
Yeah, sounds
Yeah,
That's a good idea,
I
yeah.
think people would like to have a coffee, I think. So we break until, say, 11?
That works, yeah.
Or maybe, yeah, 5
Okay, 10 minutes. We also have a drinks outside and coffee machines.
I'll make it 10 past 11, because otherwise, it's a bit, quite a group get coffee, so 10 past.
So I guess that it's depends on how many splits you do, right?
Yeah. I mean, we're going to discuss this maybe tomorrow, and then you define your score function as somehow evolving weights, and then you want modeling algorithms. And what I wanted to show next is an example where this has been done in a very nice way for a much more complex system. And what I wanted to get at was atmospheric jets. So what you see on the left is an image of Jupiter. And you see these kinds of band structures here, which correspond to strong winds that either go in the west or the eastern direction. And satellites have measured these kinds of winds in a very precise way. And a measurement of that you see on the right-hand side. This is basically, I tried to align it exactly with the planet, so that you see that this white line basically corresponds to that jet. And what you see here is the velocity in east-west direction as a function of the latitude. And you see these kind of structures that correspond to the jets that are seen here. If you look closely though, what you see is that these are actually two lines, a dark black and a somewhat slightly lighter gray line. And they correspond to measurements of Voyager in '79 and Cassini in 2000. And what you see is that it is basically unchanged over, what is it, like 20 years time. The wind speed is very constant. On the other hand, it is believed that sometime in the 40s or 50s, Jupiter did lose a jet. And that happened rather quickly. So there is a question on what's the lifetime of these jets, what's their stability, what can you expect as a typical way of transitioning in and out of them. And the simplest way to simulate such a system is some kind of Navier-Stokes equation. I'm just popping here the differential equation. This is 2D Navier-Stokes. Maybe you've come across it depending on your field, with an additional beta term, which basically is coming from the Coriolis force. So this is a partial differential equation that describes in just 2 spatial dimensions how wind evolves on a rotating planet, with very many simplifying assumptions. But you still get out, if you integrate this system in a computer, nice looking pictures such as the following, where you have these very clear band-like jet structures. The preferred direction, of course, is given by the rotation of the planet. So these large-scale structures are so-called zonal jets, and they mimic the behavior of Jupiter. So what has now been done, this is a paper by Boucher, Roland, and Simonet, is to take this system, and the first thing that we observe is, so here you see similar snapshots to the one that I showed above, but here you see a time series. This is time, and that's only the latitude component, averaging out the zonal direction, is that you observe both a state where there are 2 jets present, here there's 1 and 2, and a state where there are 3 jets present. In both cases, for very long times. I mean, it's not obvious what these units are, but these are very long times. These kinds of jets are stable. And here you see the cross section. So the green ones are, again, the mean velocity. So the green curve you could basically compare to the space probe ones. So you have this situation where maybe both 2 and 3 jets would in principle be stable, and you want to analyze in a similar manner as we discussed for the climate or for the ship capsize, how do transitions happen? How likely are they, and in what way and through what mechanisms they happen? Well, you take the system and simulate it, and you wait for days and days, and you never observe such a transition because it is so rare. So this is exactly one example where they did what I was just telling you. They defined some kind of score function, some kind of reaction coordinate, and then doubled down on those copies of the system, integrating multiple of them, that did what they wanted. And indeed, you do observe then these kinds of transition events. Here is one example from their paper, where you start off with 2 jets, and then you get the nucleation of a 3rd jet that then establishes itself over time. So here's a snapshot of the whole vorticity field at that situation. And this is like, again, a cross-section and zonal average of the velocities here. So you see there's this tiny jet that has just cropped up that will eventually establish itself as a 3rd jet. So this is particularly impressive because this system, even though it's just 2D as opposed to maybe 3D on a sphere, as you would think of Jupiter, is a very big partial differential equation. You need to resolve it on a computer with maybe 500 by 500 grid points. So it's a lot of degrees of freedom. It's much more than just like the 1 degree of freedom. And so, because the probability, for example, the probability of going from 2 to 3 jets, theoretically can be estimated to scale exponentially with some smallest parameter in the exponent, you can make this experiment. And here is the table that they show in their paper, where they say for some small alphas, which are basically just the timescale separation parameter here, comparing how long in really wall clock time they ran their ray events algorithm, as opposed to how long they ran their direct sampling algorithm, where the approximate signs are just extrapolated because they didn't run their computer for 51 years, not that they run their computer for 2000 years. So the idea here is that as you make the event more and more rare, and even though these numbers are all roughly order of magnitude 10 to the minus 3, e to the minus 10 to the minus 3 quickly becomes very big. So these events quickly become very rare, and you need to wait very long time. As soon as you do this kind of biasing algorithm, you have realistically long integration times on your computer. So this took 1 day versus 3 days. That's still completely manageable, while no chance of ever observing on this value of alpha the nucleation of a jet through some kind of naive direct Monte Carlo. All right, so this is the first half, and the first kind of way that you can think of doing this would be sampling. And the last thing that I want to get at, maybe in the last half hour or so, is a completely alternative approach, and that is large deviation theory. So the idea of large deviation theory is to skip sampling completely. I don't want to make many experiments and then select the ones. I don't want to do this kind of biasing thing even, because this still suffers from a lot of like fine-tuning. What exactly is my reaction coordinate? How do I score? How many copies do I do? And there are still fluctuations and so on. Instead, I want to compute a single deterministic event, and that should be the most likely rare event. So that sounds really weird because they are rare. What does most likely mean? But the idea is that out of all the multiple ways a rare event can happen, I want to select the single one that is most likely of. And this appears realistic because of the introductory portion that we had an hour ago, where I told you, well, if they happen, they all happen very much alike. There is this kind of transition tube. There is this commonality of what the system does in order to facilitate a rate. Can we somehow analytically compute this tube with the information of the model at hand without doing any kind of sampling? So what we are doing is we replace a sampling problem and a disadvantageous sampling problem, namely one where we throw away most of our information, with an optimization problem, arguably a complicated optimization problem, but a single one. We get an answer, we have an answer. And we always get the same answer. We don't have any variances, we don't have any error estimates and so on. So the underlying theory behind that, I think, is quite intuitive, and this is why I want to spend some time on that. And then I will hopefully show you a few examples where this can be applied. So how do you compute the probability of ending up in B when starting in A? Completely independent on what exactly is the system that I consider. I guess even coins apply. But maybe you have in mind some kind of stochastic system that you can integrate on the computer. So if it would be a simple system, maybe one where A is here and B is here, but we have some kind of screen in between that only allows for two ways to pass this, there are exactly two ways that the event can happen. You go from A through x1 to B, or you go through x2 to B. So maybe basic notion of all of probabilities theory is the probability of something to happen is the sum of all ways that it can happen, weighed by their individual probabilities. The probability of going from A to B is the probability of going from A to x1 to B, plus the probability of going from A to x2 to B. That's a rather simple system where if I knew the individual probabilities, I could just sum them up. But of course, maybe reality is a bit more complicated. If you had an arbitrary number of possibilities, you would need to sum all of them, right? I just say going from A to B is the sum of all intermediate points xi that I might consider, and then I need to sum up the individual underlying probabilities. Of course, we can do better. Imagine, for example, there are two screens. Here's a screen with a number of possibilities. Screen meaning basically a point in time where I say this thing has happened. So there are 2 points in time where I say here I choose what happened, and here I choose again what has happened. So I get two sums, right? I need to basically solve some kind of combinatorial problem where I say the probability of going from A to B is the probability of going from A to one of the x's, to one of the y's, and then to B. And I need to sum over all possible i's and all possible j's, or like even worse, it's a double sum, over all possible combinations of i's and j's. But it's still the same rule, we just sum over all possibilities, each weighed by its probability. Sorry, yeah, each weighed by its own probability. So you can do 3 screens, you get 3 sums, right? You can think of infinitely many screens. So I go to a screen x1, I have a number of choices. Then I go to a next screen and the next screen and the next screen up to xn. And I need to sum over all possible choices, which at least formally you could write at this, like it's an infinite number of sums. And then each of the probabilities need to be summed up. So if this doesn't sound scary yet, we can go further and make it a bit more scary even, because what I still had here was individual options, x1, x2, x3, just like countably many, or maybe finitely many. But in reality, what often happens is that you have kind of like a wide opening where there is a scalar number of what can happen. So here I mean this to be, I go from A to B. There is only a single point in time where I say what happened in between, and I want this to be a scalar number. Instead of summing over stuff, I need to integrate over stuff. Going from A to B, I go from A to X to B, where X is some real number, maybe between some bounds. And then I need to integrate over all possibilities X. Second screen again, double integral, right? Going from A to B means from A to x1 to x2 to B, where both x1 and x2 are possible values that I could have observed in between. So we'll recall that these are just straight lines, right? I'm only considering the process here, 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 and here, but intuitively it's still clear what I mean. I'm just saying, well, you can hit any real value between those 2 points, and then any real value between those 2 points, and then you go to B, and for each of the segments, you need to consider the probability. So last step, infinitely many screens again, and each of them allows for me to have a scalar value. This now finally fully considers every possible path connecting A to B. Because at every point in this direction, I can basically consider every point in that direction. Means that in order to go from A to B in any way that's conceivable, I need to combine infinitely many integrals
x1 to xn, n to infinity, and consider the probability of going from my point A, where I start, to some x1, which is a scalar value, to some x2, and so on, up to the final thing. This is the thing that we in the end want to do. Formally, I can easily write it down. Of course, computing it will be rather complicated. But formally, that's what we want to do. And because writing infinitely many integration signs is a bit awkward, there is a notation for that. It's called the path integral. So I replace it with a single integration sign, but I no longer call it dx, I call it capital dx with square brackets because functional dependence and so on. But x is supposed to be a path now. So any of these x's is a full discretization of what my system can do. I weigh it with its respective probability, whatever that precisely means, and I integrate from the point A to the point B. So formally, this is clearly a true answer, saying, well, how likely is it to go from A to B is, well, you just add up all possibilities that it can happen. There are a lot, but you add up all the possibilities and weigh them with their respective probability. That's exactly what we want to do. So in some sense, all of these questions are answered. What's the likelihood of a rogue wave? Well, all ways the rogue wave can happen, weighed by its probability. There you go. What's the likelihood of transitioning from a snowball Earth to a warm Earth? Same thing, right? This is all that you need to do. There remains the problem, of course, namely what's the probability of a certain realization of the path. But for a large class of systems, this can be answered. What's the probability to observe a given path x? So we have a stochastic system of this form. X dot is some f plus some noise. And I want to consider white and time Gaussian randomness. So even if you've not come across stochastic differential equations, I still think this is fairly intuitive, if as long as you have taken like probability A and know about Gaussian random variables. What's the probability of observing any Gaussian scalar variable? Well, it has a density of e to the minus x squared over 2. That's like the Gaussian bell curve. That's the probability of observing a single random variable that has a Gaussian distribution. What's the probability density of two independent Gaussian random variables, x and y? It's the same, just in the exponent I need to add the squares. And you can do that for vectors and say, what's the probability density of n Gaussian random variables? Well, it's sum. And then with a leap of faith, you say, formally, the probability of observing any Gaussian random noise is e to the sum of the squares of the individual components squared and then integrated over time. So what I'm saying formally, and it turns out to be true in a certain rigorous sense, is that a Brownian motion is nothing but infinitely many Gaussian increments. At every point in time, I'm drawing a normally distributed random number, and then I add them all up. That's the density. So if I then go ahead and say, solve for eta, this equation, well, eta is x dot minus f, and here I go. That's the density of observing a certain path. If x dot is f plus eta, and I know the density of observing a certain random fluctuation, I know the density of observing the corresponding path. I just solve it for x. So the probability density of observing a certain path x is e to minus 1/2, and then I integrate the square of the difference between x dot and f. Basically saying x dot equal f would be what I would observe for my system if there would be any stochastic noise. Well, x dot minus f is non-zero is exactly the contribution of the noise, and the contribution of the noise is Gaussian. This is the probability density. So we are a huge step further, because now we can write down the whole thing, at least formally. The probability for any stochastic system to go from A to B is just integrating over all paths this density in path space. And because this is a bit awkward looking term, I just replace this with a signifier S, which in physics is often called the action. In probability, it would be called the rate function. And if you've heard action before, because you're a physicist coming maybe from quantum mechanics, quantum field theory, or stochastic field theory, it's exactly the same meaning. And similar intuitions apply. So this is all great. I still use this. This was just fancy notation for infinitely many integral signs. You can do nothing with this. You cannot compute it. So this is not helpful. Formally, it's true. Formally, it's saying, okay, I know the individual contribution of each path there are infinitely many of them. They all have like an infinitesimal contribution to probability. So just sum them up means nothing, right? But here's where the helpful thing comes in from the rare events. If we now say, let's make the event rare, and I will do that in a specific way. There are many other ways of doing it, but I do it in a specific way. I do, for my differential equation, I put the smallest parameter in front of the noise. The smaller the noise, the less likely is it to not do the thing that the differential equation wants. In the limit of the noise going to 0, the only thing that survives is what the system wants to do it on its own. So if I wanted to do something very extreme away from the typical behavior, the smaller the noise, the less likely it is. I can just insert this in the same thing. You will get out the same answer, just that you have a 1 over epsilon in front of the exponent, because of I chose to scale to the square root here. So the end form is the same, just that I have the smallest parameter in front of the action. So what do we gain? If you've come across physics, you immediately know what you gain. If you have the smallest parameter, you can approximate the integral. And that's exactly the idea that we want to do. Maybe the thing that you have come across, depending on your background, is the so-called Laplace method. If not, it's not too difficult to grasp. If you have any kind of integral of this form, an integral where the integrand is the exponential function of some other function, but you have this construct of 1 over epsilon in front, and you let epsilon go to 0, then this can be approximated with e to the same function, but evaluated at the minimum of x, at the minimum of f. This is the so-called Laplace method. You can derive this in 2 lines, so I will. Why is that the case? Well, if you expand f around the minimum, x star being the minimum of f, so f of x star plus h is just f of x star. This is a Taylor expansion plus h f prime plus 1/2 h squared f double prime and so on. We know that f prime is 0 because we're at the minimum, like I guess differentiability and so on, but f prime being 0 because this is the minimum, then I can replace this integral by the integral evaluated at the minimum plus h squared, this term is the next one that applies, f double prime. This one is now a simple Gaussian integral, this just amounts to some kind of integration constant that I don't care about. The relevant part is the one in front here. So in the limit of epsilon to 0, this Taylor approximation becomes better and better. This constant I don't care for, it's just the exponential scaling of the probability that I want. And exactly a similar argument was used for the jets, where I said this scales roughly like e to the minus alpha to the minus 1, is here as well with the epsilon. So we want to do exactly that for the path integral. That's maybe a non-trivial jump going from a 1-dimensional integral to an infinite dimensional integral, but still that's what you do, or that's what physicists do nevertheless, saying that the probability of going from a to b of this function in the limit of the event becoming more and more rare can be approximated by the exponential of the action evaluated only at the most likely, that is the minimal action realization of it. So x star solves this minimization problem that minimizes the action. A physicist would say this is a semi-classical trajectory. A mathematician would say this is the large deviation minimizer. Often this is called the instanton, because coming from, I guess, quantum chromodynamics and quantum field theory, the minimizing path of the action. Maybe that's a bit too technical. What I want to say is the main problem that remains is to find this minimizer, to find this instanton trajectory x star, such that the action evaluated at x star is exactly the minimum of the action over all possible paths. And this is the optimization problem that I was talking about earlier. And it's also very intuitive. If you look at this double well, kind of like transition tube thing, the white path is exactly this instanton. This is the most likely way of realizing the transition from that point to that point. And it goes exactly at the center of this transition tube, or roughly at the center. But the rigorous thing is that as I would let the noise become smaller and smaller, all of this cloud would concentrate on a single trajectory, and this white one is this single trajectory. The less likely the event becomes, the more similar it becomes to the white one. And you have strong rigorous statements about, in the limit of the event becoming infinitely unlikely, it must happen that way. So what do we gain? If we compute this optimal trajectory by solving the optimization problem, you can estimate the probability of the event, because it scales like e to the action evaluated at the instanton. But you can also kind of like predict the most likely occurrence. We get the tube, or we get this, the center of the tube, or the relevant information about the tube. Meaning you could explore causes of something like that. If you go from Snowball Earth to warm Earth, in what way will it happen, right? All the other ways are exponentially less likely to occur than this one in the limit. And maybe lastly, what's the most effective way to force the event? All of that is assuming some kind of stochasticity, so you can invert the problem and say, I want this to happen. How do I most efficiently prod my system so that it does happen? Or what kind of noise do I need to prevent to make it less likely to happen? Some kind of optimal control problem. Okay, so this is the alternative approach, and this is called large deviation theory for stochastic processes, sample path large deviations, or maybe instanton calculus and path integral formulas. So a very simple example for that, I start with an STE that's just linear, an Ornstein-Uhlenbeck process. Then you can compute this instanton on paper. This is the optimal path to realize a certain high event set. So before I showed you with the cloning, some paths that did and some paths that didn't do something, then we did this biasing procedure with the cloning. Here I just compute, okay, the event should be hit 1. This new star is the most likely way to hit this 1. And it just comes out of solving a constraint optimization problem where I say, what's the most likely way of minimizing the corresponding action of all trajectories that start at 0 and end at 1? So there are infinitely many trajectories that do this, but one of them will minimize the action, and it is the light blue one that minimizes the action. So this is a treatable optimization problem because it's a fairly simple system. This is why I can write down the solution analytically, but I can still do numerical experiment and I observe a very similar thing. So this is a point cloud similar to the one that I showed for the capsite problem, just this time this process, starting at 0 and ending at 1. All the others I threw away. So I did like 10 million experiments again, similar to the coins, and I only kept those to what I want. And this point cloud basically says, these are all trajectories that did it. What you see in white superposed is the instanton trajectory that's given by that. And maybe even more strongly, you could then go ahead and say, okay, what's the average way that this event happens? So I average on the blue point cloud, and you get this blue line. So the average way that the rare event happens looks very neatly like the solution of the optimization problem, or like the instanton that I was talking about. So I want to now get back to this rogue wave problem that I hinted at the beginning, as one as the exemplary problems where this can be applied, but maybe you get the hint. What I showed you somewhere here is I said something like, whenever the wave happens, it happens in a similar manner. This applies to the whole transition tube. There is like a volume around my rogue wave that is most likely hit. So now we can make this a bit more precise, basically saying, do these trajectories look like the corresponding instanton? Do they look like the corresponding solution of the optimization problem that corresponds to the most likely way of observing such a problem? And we do that this time, not for any numerical simulation, but exactly for the data that's coming out of the wave flume experiment. So this is really recorded data by the individual probes. You know how this event looks like, and I can compare this to an analytical solution that is the result of an optimization procedure, of course done on a computer, that gives you the most likely path of that. So here's the build-up. You don't need to understand the whole equations. I just wanted to flash what I'm using. We estimate the evolution of the waves to act according to the so-called nonlinear Schrödinger equation, which describes the evolution of a wave field across the flume. You can define what the surface elevation looks like. And then we have exactly this instanton computation situation where I say an equation as I had before, just my deterministic part is the nonlinear Schrödinger equation. My random part is this John swap random initial distribution that I plug in. That was the random distribution of initial C states that was measured. And the observable that I want to estimate is somehow the maximum elevation. So what we want to find at the end numerically is exactly of the form that I showed earlier, the probability of the maximal elevation exceeding a threshold. And if the stuff that I told you it would be true, this should scale exponentially, where in the exponent I have some kind of action evaluated at the instant. That should be the probability scaling, if that applies. It should apply in the limit of the event becoming more and more rare, meaning in the limit of the amplitude of the wave becoming higher and higher. And maybe more crucially, we can compare this instanton trajectory to the actual observed one in the wave, or to all of them. So we can compare not only the probabilities of them, we can compare the actual trajectories. And this is what I show here. This is a bit of a multitude of plots, but I told you earlier that the initial condition that we plug in, that is the random C state that we plug in, comes with different parameters, the significant wave height and how nonlinear the system is. And here the three colors correspond to different nonlinearity of the field. So each of those correspond to a separate experiment. And then the different lines are just which probes I'm looking at, 10 meter, 30 meter, 45 meter as before. So that's where we observe the rogue wave event. And I think I've shown you that one earlier. But now I have it also for a very linear system, for a highly nonlinear system, and for something in between. So color, solid line, and color background shading is again the experiment plus minus one standard deviation, while black is now everywhere here, this instanton solution that is the outcome of the optimization problem. So for example, taking this one, blue, which is wobbly because it comes out of an experiment and has a standard deviation because there are many of them, has a certain shape of a wave, and black is saying the most likely way of realizing this wave is this black. And you see that they very neatly agree, not only at the end, but throughout their whole evolution, at least to a degree. There might be some phase shifts here, but you clearly see that they are behaving physically in a similar way. And this holds true throughout for different parameters of my C, meaning maybe a more rough C and maybe a more mild C. In all of these cases, the ray event is most likely described by this instanton realization. So this is particularly nice, and this is exactly the way that I was trying to hint at earlier. They all happen alike, and we have a precise understanding of which event is the one that should be the most likely. And we can compute it. Of course, we can also try to do the same for the probabilities. So what I'm showing here is rescaled to not the wave channel, but actual C data, likelihood data of observing a certain wave height. So this is the wave height in meter, and that's the corresponding likelihood. And for this C state, which is called a rough C and it's called a high C, there are certain rogue wave threshold of the regime, and this is saying how likely would be a rogue wave of a certain height waiting a certain amount of time. So for two different kind of parameters, this is more rough, therefore the waves are higher here. Rogue wave would start at 16 meters, and here it does at 7 meters or so, maybe even lower. So this is coming from measurements. We observe only a handful, I guess 1 or 2 of these events, and many more here. And these solid lines here are coming from large deviation theory. So these are coming from instead plugging in e to the minus the action at the instant. And you see that this clearly fails for common events, and it clearly works excellently in the far tails. So because luckily for the rogue wave problem, we are exactly interested in the most extreme and the most rare events, this works best. It's really like an inversion of what you would naively and usually assume, that the more likely an event is, the better we can treat it. Here, the less likely an event is, the better we can treat it. And we have guarantees, provable, rigorous guarantees on, in the limit of this going to infinity, how the event should look like. Because there, the discrepancies become exponentially unlikely, so these predictions become better and better we further go into it. That's a very rare situation to be in, but clearly they already are good, exactly starting at roughly the rogue wave threshold, which corresponds to 8 sigma or something, as I said. So that's rare enough for this to apply. So we can nicely predict the tails and therefore the probabilities of these rogue wave events in this regime. Great. So the last example that I wanted to show is an even bigger system. This is the full 3D Navier-Stokes equation. So maybe this is only now for the physicists and mathematicians in the audience, but that's the 3D Navier-Stokes equation, which basically describes the evolution of an incompressible fluid in a large volume. And it's like considered an important question, both because of its mathematical beauty and importance, but also because it describes fundamental aspects of turbulence that is present in any kind of flow, like your blood or the atmosphere or star formation on any kind of scales. This equation is relevant. And we can ask similar questions like, what's the most likely way that an extreme vorticity or an extreme strain event will happen? So you can again solve the corresponding optimization problem. For that, you would need to solve the so-called instanton equations, which on Thursday we will discuss in more detail. And if you solve them, you get out an event and you can compare it to direct sampling. So that's the thing that I want to show here. I'm interested in events of a certain vorticity, meaning in terms of there are vortices that are very strong. And I want to compare the instanton prediction against stochastic DNS, that is stochastic direct numerical simulations of the same stochastic system. So this problem is very large. The way that we solved it is in a 3-dimensional volume of fluid, which needs to be discretized with maybe 128 or even more grid points, and maybe 1,000 degrees of freedom in time. So this is like 10 to the 3 to the power 3 times 10 to the 4. What is it, like 10 to the 13 or so degrees of freedom? It's a very big optimization. It quickly becomes problematic to solve itself. But this is supposed to doing like trillions of experiments instead, if you wouldn't be able to do that. So we can directly compare that, and this is, I mean, maybe not commensurate to the amount of effort that I just sold you on, is the outcome of the most likely vortex in Navier-Stokes. So if I want a very high vorticity at the central point, this is the most efficient way of doing it. It's some kind of vortex filament that has some kind of rotating components around. But maybe the most important thing is that you can compare this instanton realization again to stochastic averages coming out of the actual simulation. So I'm just doing a lot of experiments. This is, of course, for a parameter set where you still can observe them. And then you average the events coming out of the transition tubes, similar to what I showed earlier for the rogue waves or for the simple system, and they look very much alike. Okay, so I think it makes sense to skip the rest and come to the summary, because these systems are a bit too technical, maybe. And say the following. What I try to get across in this talk is that relevance are often relevant, in particular if their impact is so big that even their low probability makes us want to consider them. And they also necessitate special methods. And I showed you basically 2 classes of methods to deal with them. One of them is sampling, but sampling in a smart, non-naive way. This includes importance sampling, these cloning type algorithms, and so on. And these will be discussed tomorrow in more detail, including Blackboard, I guess. And another class is, instead of simulating the whole system, we instead compute a prototypical placeholder optimal event. This is large deviation theory, and this we will discuss in more detail on Thursday. So these are applicable to many systems of high complexity. Here are a few that I dealt with, like fiber optics, active matter and bacterial motion, climate, and we saw the ship capsize and the atmospheric jets, maybe also plasma reactors and fusion, plasma confinement, and so on. And with this, I thank you for your attention.
Thank you very much. It was very nice, very clear. Any questions? Yes.
Yeah, I was wondering how large deviation theory could help you if you want to know more about an unlikely rare event instead of the most likely rare event.
So you are saying there is an event that you care about going from A to B. There are multiple ways of realizing it. One of these ways will be more likely than the others, but how can you learn about the less likely way of realizing it? So the answer of large deviation theory is you shouldn't care about the less likely one, because it would be completely dominated and like astronomically dominated by the more likely one, such that in the limit, it's only the most likely. You can sometimes have, because of symmetry, multiple ones that have equal weight. These problems are known in optimization in general. You don't have a single minimizer, you have maybe a couple of minimizers, maybe even have a whole continuous family of minimizers. These can be dealt with the same method, with a few additional bells and whistles. I skipped that part, but it can be done. But one that's not the optimum, you shouldn't care, because it can't contribute in the limit. If you're not in the limit, the whole theory doesn't really apply, but then you don't deal with ray events, right?
Okay, thanks. Any other questions? Yeah.
Maybe I have the start of a question. So your notion of how to deal with this is based on the states of the system, and there's this path between these states, and the path is narrow. It's kind of you can meaningfully limit the range around that path. So
This is for the second half.
our prime minister would call that a goat's path.
Okay.
Not enough Dutch people to understand that joke, but is there any? So it's kind of attractive to think that if you are in the system, that you could actually see that you are on this narrow path towards the other state, right? Because a state transition is often like a dramatic event.
Yes.
Is there any theory around that, or is
Yes, so this is included in what I was saying. I didn't highlight that, but if you consider any stochastic system like the economy or the climate, I mean, assuming that your modeling assumptions are correct, because of course all of this implies that whatever equation you have on paper has some notion of realism to it. But as long as you observe that, then you can say, I want to avoid going in this to this particular endpoint. Here's the most likely way that I would go to it, and look at that. I am on this path. I'm currently not at the typical point of the system, but I'm already departing from it in a direction that is somehow compatible with the most likely one given here. So while this should ring alarm bells, this has still not the predictive power that you might think. Because what I have been saying is that conditioned on ending up at B, this is the most likely path to go. Sure. But conditioned on being here, it's still unlikely to reach B. So the only thing that you can derive from that, but that's powerful enough already, is if you are not on this path, you will definitely not go to. You must be on the path in order to go to, right, in the right limits and everything, but there is no alternative, right? So at least you can say, oh, I fear of going to B, and look, here's what I am. I'm not at all on the most likely path, then it's exponentially unlikely to happen. So this is already worth something, but it's not true that you can say, maybe not necessary, just because I already did something that looks like this instanton, it is somehow very likely. Because not doing it is even more likely. All of these events are very unlikely, right? These instanton paths that I showed, they happen 1 in 10 million times. So if I'm going the first few steps of it, it's like saying, okay, the way to throw 100 heads with coins is always throwing heads. Oh no, I already threw 2 heads. I'm on the path to 100 heads. Is a fallacy, right? Yeah. But if you have thrown 2 tails, you're definitely not gonna get 100 heads.
Thanks. Yeah.
Could you go back to the slides where you showed the graphs of, you showed that the data were much more,
Which one? The
agreement before, this is the one, right?
This?
So no, one after, yes. And I think if I did correctly, it is exponential, right? At least in the limit.
Right, yeah.
So
this is really, but they are a bit more complicated because there's like a nonlinear system somewhere in between.
Because you mentioned financial markets, these graphs are in the financial markets are known to be either two forms I know of. One is a power law, other one is a stressed exponential. So I was just wondering, because you made a remark that something else will also, the same procedure will also work, for example, financial markets. Is that really correct?
So I think what you're referring to is a subfield that I completely did not touch, which is extreme value theory. And you have a distribution of random variables, and you want to conclude the distribution of its extremes. The difference between that field and everything I told you here is that I'm usually considering complex systems somewhere in the mix in between. I'm giving in statistics into the wave equation at the initial point, but then I'm propagating that with a complicated nonlinear system, in this case, nonlinear Schrödinger equation, or some kind of reality, and the outcome can be arbitrary. So while there might still be some universality to what the tail scaling must be for the extreme values, here I get a much more precise handle on what the probability distributions become as they are deformed by a complex stochastic differential equation. So while maybe you can deduce what they should look like if your system is linear or you have other kinds of guarantees on your system, then you probably get some kind of universal scaling laws that are known.
Yeah, market systems are very, very, very nonlinear.
Yeah, okay, yeah.
That will not work.
But also with a lot of different noise.
Well, I
This is Gaussian
suspect
noise.
I suspect the difference here is between what we call complex physical systems, where we have the tendency to put all this Gaussian noise, and complex adaptive systems, which are highly coupled, highly correlated, and all of these things. Agents, I mean, if a market starts to crash, agents will anticipate a crash happening and act accordingly, and that brings these correlations, very long time correlations.
Yeah, so I didn't show any examples of non-white in time Gaussian noise, but you can easily depart from Gaussianity, also from like Markovianity with these kinds of systems, at least in a multitude of special cases. Like Levy noise has been done, temporal correlations for Gaussian noise has been done, and so on. But I mean, they go a bit beyond the easy systems that we're considering here, but it's doable. Any kind of strong coupling in the deterministic part of the equation is intrinsically included, and that's what makes the strength of this method, right? In a sense, often if you do some kind of perturbation theory, you're saying, look at this very complicated system, assume that the nonlinearity is small, or assume that the amplitudes are small, and then slowly put in back the nonlinearity perturbatively. This here is completely the opposite idea. There is a nonlinearity, it's strong, it's fully considered, and the interaction between the noise and the nonlinearity is strongly considered. And the limiting thing, the thing that's small that you perturb around, is the probability of the event itself, right? I'm saying as soon as the event is very unlikely, it becomes predictable again. That's I guess the major takeaway.
Is there any studies on sensitivity to model error? I mean, because this looks
Right.
like that it might be very sensitive. In the action, if you have
Yeah.
an error there, it's sort of blown up by this noise, small noise. I mean, in the examples you showed, that's not so relevant, but in many models which you use in the real world, I mean, there's errors there.
I don't know of any studies. I don't think it's easy to make generalized statements about that, but I can imagine that there are many systems where this is crucially problematic. So I very rarely touch reality, I must admit. So the roadways were the only case where I did. You have provable guarantees if I know that the equation is correct. But if you're saying, okay, there's uncertainty on the drift term, of, for example, the deterministic portions or the nature of the stochastic noise, you might get large errors because you're dealing with very small probabilities and very extreme outliers. Yeah, it's a very important point. So of course, maybe I made the point very strongly here that we get predictive power, but reality is complicated, right? I mean, I say provably this is the limiting thing, but only within the realm of mathematics, right? Not necessarily as applied to a proper wave in a proper ocean where there's wind and wave breaking and currents and ships.
Any last question? Yes.
Just to be clear, because you made from going to the action, you made the approximation that it's Gaussian, but I just heard you said it will also work for Levy processes as well.
So I made a hand-wavy argument on that, the probability density of your stochastic forcing. This was e to the eta squared, right? I don't want to switch to it. If you have, for example, time covariances, time correlations, you instead get a temporal kernel that they need to that you need to convolve with. For Levy, it's a bit more complicated. You probably get different exponents and square. The square that I had in there is, of course, the Gaussian in the end. So if you have alpha stable Levy, you get, I guess, an alpha there.
Okay, well, thank you very much, Tobias, for this first. We're looking forward to listen to you tomorrow at 10 o'clock, again here in the same room. And we're looking forward to see you then too. Okay, thanks.